So welcome to this last presentation of the day. Oops. Yes. So I will talk about nonification. So non, it's known, so it's the theory of nothing. So thank you, it's finished. But non could also be 9. So we will see what we can do with 9 coordinates. So yes, I will present again. I already presented a part of this 9 coordinate system at Prague group 32, but here I will give more detail and a lot more detail to show how with this theory we can have the standard model and a unification theory, which emerged very naturally in the 9-dimension representation of E8. And it's really close to the theory that Piero presented. You will see the difference. So this is a part about the group theory. So it's good because with all the presentation we had before, I can go a little faster on this. You already understand the symbolic and the notions. And at the end, I have 2 important slides where I will show how we can use this here at QGR. In fact, it's 2 ongoing projects in 2 different approaches. The tensor network, so how I can go from E8 to tensors in a tensor network approach, and also how I can go to E8 to spin networks in a loop quantum gravity approach. And you will also see that my E8 model comes from string theory. So we are associating string and loop quantum gravity, and also this new approach, tensor network, which is more like quantum computing. And what is good is this, with these 2 networks, we are really matching with our tool developed here on quasi-crystals, and also using the E8 lattice for the Elzer-Sloan quasi-crystal to generate geometrically these networks on which we will implement the particles. And this is why also we have 9 coordinates. Because of this citation from a quite old book from 82, A Unity of Forces in the Universe by Anthony Z, which is a professor of physics at Kavli Institute near here. And he concluded the chapter 1 on exceptional unification by this sentence: "It is amusing to speculate on the possibility of a theory based on E9." So we will speculate and we will try to be amusing. So E9, you know, E9 has a Lie algebra. This is the affine extension of E8 and has an infinite number of roots. And the roots are the weight of E8. In fact, the roots of E9 are the points in the E8 lattice. So this is why we confuse the 2 objects, because this is only one, the E8 lattice, and the E9 roots algebra, roots of the algebra.
So can I say more or less that when I think of the E8 lattice, when I want to think of its algebraic analog, I should think of the E9 Lie algebra?
It's correct. It's more correct, but many people are not understanding this. So,
okay.
So you can say it if you explain it.
Okay.
Yes, right. But I think it's still important for us because we are using all these points which are weight in representation in a classical view of Lie algebra, but we are using them more geometrically, so it's maybe more as roots of E9. Also with the 9-dimensional coordinate, we have a 9 again, but the Lie algebra which is behind there, is still E8 Lie algebra, E8 Lie group, without any doubt. And in fact, yes, except being able to go to the affine space, so to integrate all the translation, not only the rotation but the translation, which is a definition of an affine transformation. There is nothing more that I can say about what E9 is bringing. But really, we are working on the affine, and we are projecting it to the quasi-crystal. But locally, everywhere, we have the symmetries of E8. So we have E8 particles. Also, we dedicate this talk to Piero Truini. Thank you for coming here to celebrate your retirement and a career of great works on E8. And probably it's not the end, it's just the beginning of the hard and the serious work. And also, thank you to Mike for organizing this 5th AQC, Advance in Quantum Gravity. And thank you for Cliff for hosting all of us in this marvelous place. And thank you to all of you for your attention. But I have not finished, but because at the end, Fang will have to go, I will rush and I will not have the time to thank you. So it begins with the idea of the partition of the E8 lattice into 3 lattices, an idea that Klee pushed strongly since some years, and that we realized only recently. But I will show you how now with the 9-dimension coordinate, everything is more clear about the unification theory and without supersymmetry, because I want to avoid supersymmetry. So any AN algebra root system or any AN simplex lattice coordinates are expressed in n+1 dimension, just with the condition that the sum of the n+1 coordinate cancels. So then E8 is the superposition of 3 A8 that I named A81, A80, A81, A82. And one of them is the ordinary A8 lattice, this one with 12 roots. And we know that there, so I have a 3 because I put a factor 3 to the ordinary coordinate. So generally it's written as 1 minus 1, and I have 7, 0 from the 9 coordinate. I have 1 times 1, 1 times minus 1, 7 times 0, but I multiply all by 3, because here I will to have all integer. And so this is the roots of polytope of A8 and the root lattice. The other roots of E8, so there is 2 times 84 other roots. Their coordinate are the permutation of -2 3 times and 1 6 times, which will have a sum which is 0. And they are grouped together, so they are congruent to 1 modulo 3. But they are not a root lattice because the 0 is not in it. The center 0 is not in. In fact, the lattice built on these fundamental vectors is the same as this one, translated by 1/3 of one of the vector of this lattice. This is just geometrically. You take the A8 lattice, you take one vector, and you translate by 1/3 in one direction, it gives this, and 1/3 in the other direction, it gives this. And then you have a 3 periodicity along all of these lines.
Ray, I have a question. Do you have an analogous construction for the other exceptional root lattices?
Yes, for E6. This is just what we will see.
47?
I don't have it, but I think that yes, there is
some
some relationship.
Construction.
Yes, but E7, I think you have to fix 1, so it's no more so symmetric.
Yeah, because in probably you need a semi-simple symmetry, because now you have A8.
Mhm.
46 probably you will have. What will be the analog? 46.
Oh, E6 is there. It's just what I will present. E6
Okay.
obey exactly
Okay,
to
okay.
the same system of coordinate, and it's just a subset of the roots of E8 that I presented before. So first, why? This is because E8 can be decomposed as A2 and E6. So this is a maximal subgroup of E8, A2 cross E6, or plus here. And A2 is SU3, and I put a F here for family. So this is where my model is different from Pierrot's model, because Pierrot used the color here. But Pierrot is also using a first subgroup where decomposition of E8 into his maximal subgroup, which is A2 and E6. So it's a A2F plus E6. And then when I decompose the representation of E8 in these two subgroups, so the first number in the parenthesis is the component on SU3, and the second is the component on E6. So I have a complete E6 here. There will be the boson. Here I have a complete SU3, which is the family boson outside of E6. And here I have 27 plates, or I don't know, yes, sets of 27. And I will detail after what they are. But Pierrot has also the same, and in Pierrot's model, it's clearly the Jordan pairs.
Yes, exactly.
Yes. So.
Yeah, 3 Jordan pairs.
Yes.
Sorry, Ray. Very often I show the magic star projecting on the what I call the color SU3, so to say.
Yes.
But that holds for all the SU3s you want. So
Yes.
it could be this one as well. I mean,
Yes, right.
It's not
Yes.
that I prefer the colored one. It's more pictorial. So that's why I show that usually. But you can project on any of the 4 orthogonal SU3s, and you
Yes,
you
right.
get the magic star in any case, and it's exactly this.
Mm-hmm.
So it's not a difference with respect to mine.
Yes,
it's a
right.
difference.
Yes, right.
Okay.
So here we see I represent the 9 coordinates of one root vector of E8 by a square. And if it's gray, it's a 0 coordinate. If it's red, it's 3. If it's cyan, it's -3. So here, there are elements of the 72, which are also roots of A8. But you can see that this 6-1 are also the 6th root of one A2. This 6-1 are the 6th root of another A2, because they are perpendicular. And this 6-1 are the 3rd A2. So this is why I present this to you, in fact, and name it nonification, because you have really 3 A2 which emerge directly in E8 from the 9-dimensional coordinate, and this is new. But the model that I'm using here is the same than yours, yes. And but the way it emerged, I have 3 which are emerging, and the 4th one, it's more difficult. It's a little embedded everywhere because it's outside of E6.
So can these different A2s form some kind of order sets, so they can represent another parameter like time or something?
No, they are used to make the standard model. And in fact, the 3 A2 together, the product of 3 A2, is the group, the gauge group of trinification, which was a unification proposed several years ago. And this is from this that I use the name nonification instead of trinification, because I have more 3 in this series than in trinification. Trinification begins just with 3 A2. Here I show how these 3 A2 are coming thanks to 3 and 9 from the E8 naturally, and then to the E6. So we really have something interesting. And this 3A2 will be in the order A2 left, A2 color, and A2 right. So you can also think of this as center, so it's easy to see this. And for the three chords, in the first three-dimensional space, you have the A2 left, which lives, and the color, the gluons are here, and this is the other bosons which generate the weak force. I will show this after, but there is many reference to show this with more detail. I will give a little detail on this. But I also have 27 other, so it's interesting to see 27 other roots of E8, which are also roots of A8, and in fact, and also of E6. So they are the intersection of E6 and the A8, but the A8 one, so the translated A8, in fact, yes, it's not roots of A8. And the coordinate are represented, the blue is 1, and the magenta is -2. So it's all the possible permutation where you have at each line 1 magenta and 2 blue. But they are all different. So each line sums to 0, then it belongs to E6. And they are the leptoquark boson in the E6 unification theory and in the trinification theory. And this leptoquark boson are so physically we don't know them, but they are transforming lepton in quark and quark in antiquark cyclically. So we need them to have the theory. But there is mechanism of symmetry breaking and Higgs mechanism which gives very high mass to this boson, explaining why we don't observe them. And so their opposite, their antiparticle, are here. So now I hope that you see clearly from 9 coordinates how you can get all these groups, E6, E8, and the 3SU3. Is it clear, or is there some question on this? All right, so good. So this is explaining also what are these bosons in a terminology of representation theory. So these 78 bosons of E6, which can act on E8, are the groups, the 8 groups that are represented. So in fact, the 811, for example, was this one. And then you have the 181, and here you have the 118. And this one is a 333, and this one is a 3 bar, 3 bar, 3 bar, leptoquarks here. And I use B for boson, boson left, boson color, boson right, and B bar. Then these are the fermions in this model, very simple. The quarks, the antiquarks, and the boson. And the quark have 2 indices. Alpha is the left in this index, and beta is the right index, and gamma is the color index. So the quark and the antiquark have color, so they have 1 left index, 1 color. So they are the left quarks, this first family, 3 bar 1. And they are 9 because it's 3 times 9, 9 quarks. The same for the other. And this one have no color index.
So 1 here means a singlet?
Yes. Yes, a singlet in the right color, for example, here.
Just to mention, Ray, that exactly the composition of the 27 has been used to connect E6 to the quantum entanglement of 3 Q-treats.
Oh yes,
The
also
bipartite entanglement of 3 Q-treats. So there is this nice connection between exceptional symmetries and quantum information. And so, in a sense, there is a direct translation between the quantum entanglement of the bipartite quantum entanglement of 3 Q-treats and the trinification field model.
Oh, that will help a lot in my part on tensor networks. Okay. Because this is in tensor networks that we have these 27 matrices, but we will also have the formalization of quantum computing.
Exactly,
yes.
And the same for E8, of course.
Can you repeat?
Yeah, I mean, what I mean is that there is an analogous description of E8 as describing some entanglement of a certain number of 4 Q-treats, because it contained three copies of A2. So I mean, again, there might be a relation between your nonification model and the quantum information picture.
Oh yes.
Probably it will have some relevance for your tensor networks. That's what I mean.
Yeah.
With the 4, yes.
That sounds very interesting.
Yes. Interesting. So this
first slide. What do you mean by ends? Is that exactly?
Oh yes, this is a model from E6 unification and trinification. There are specific leptons which is also non-observed, which are neutral. These are neutral leptons, so we don't observe them. So they should have very high mass if the model is correct.
So if they are they are single leptons. They are not attached with neutrinos.
No, the neutrino are here. I have only one family here, and I have the neutrino and the antineutrino. So
these leptons are like single leptons.
Singlet.
Yes, only singlets. Yes, okay. Yes, and there is two charged lepton, which also doesn't exist. Mm-hmm. And also there is a family of a third quark. We have up and down, and another which is sometimes named H, which also is not observed because it has very high masses, but it has the same charge and D, minus 1/3. So yes, there is some problem in this model. There is some too much boson and too much particles, but there is a mechanism which are very well explained to give them very high mass and explain that we cannot observe, and also to forbid the proton decay, which are the two problems. But I'm still not sure that it is really solved, but there is problem who were exhibited, and there was many kind of solutions to this. But this is still, so I will say the model is waiting for something to really re-emerge after the initial work of Gursey, yes, Feza-Gursey. And it's similar, the E6 model is quite similar with the E8 model used in heterotic string theory by Witten also. So we see with this model, Pierrot's model, Tony's model, Garrett, there is some model, and the new one also that you presented. So maybe we can have 5, 10 different models. What I'm sure it's one of the model is good, and this is an E8 model, but we have some degree of freedom to explore different model and exchange, and this is good. But
I was just going to ask: Are all these particles in here fermions in the Qs?
Yes. Here
so
are just the fermions.
How many fermionic degrees of freedom are you having in E8 here?
27 times 6.
Okay.
Fermion? No.
Fermion.
Those are bosons.
And 78 bosons, yes. The 27 are the fermion here.
Oh, they're all fermionic, including the
yes,
last.
And the boson, I don't show the matrices because I show them before they were represented graphically by the coordinates. The leptoquarks, the gluons, and two other family which serve to generate the W and the Higgs boson by the mechanism of symmetry breaking between these two SU3 to the standard model. And I will show this. This mechanism is on this slide.
Sorry.
Yes. It breaks the fermions to give them the charge with C, SU2L, and U1. I didn't give the detail of the boson, the name of the boson themselves, but there is literature on this. Yes?
You have a strangest charge here. It's 1/6.
Yes, it's not the electric charge, it's the Y charge.
White charge?
Yes.
So Ray, you said that there's three of them because the mass is too heavy, so we don't measure them. Is that just your conjecture, or you have something to
It's the way
show?
all physicists are doing with a unification model.
So anything that is not there
hide
because they can't measure
the
it.
trouble under the carpet.
Or
so
they say
they're
that
too
we
massive.
will discover it with proper technology.
Is beyond experimental
Maybe the mass is
falsification.
Except maybe David's model doesn't have any particle that we have to make disappear. Oh, that's great.
Yeah, I was just going to say this model is similar to Todorov and Dubois-Violette in the sense that they assign all of the octonions to fermion in the J3Os to fermions. The only reason I didn't do that was, well, first because of the 128 seemed to be a nice spinorial dimension, but also we had this intuition of triality and relating bosons and fermions, so it seemed natural to think of 16 plus 10 plus 1 and only have 16 degrees of freedom with fermions. I'm not saying that's the only way to do it, but
yes.
It just seems if you're trying to introduce these additional quarks and then remove them, you know, why even introduce them in the first place, I guess. But just something to think about.
Okay.
Yes, Piero, yes.
Okay. No, here I see the difference with what I'm doing.
Oh, yes.
And that's a very big difference. Because it's related to what David was saying. It's not only that you want to associate, you like to associate fermions to spinors. It's because actually, when you have fermions and spinors, of course you have first of all to decide what is your dynamics, because if you don't do that, you're just classifying things and you don't know what you're doing with those. So first of all, it depends on the model you have for your dynamics, otherwise you don't do nothing. Once you say that the dynamics, for instance, as in my case, is given by the elementary interactions which are just the commutators, then the spinors have to be fermions and the bosons have to be the other ones. Otherwise, you would have two spinors going into a spinor. So you violate, you see, and that cannot happen. So that's the real reason why 12
Or 28.
have to be, or 28 if you include if you include the cartons. No, the 128 would be the fermionic.
You're talking about the bosons, yeah.
Yeah, and the bosonic would be the other one. The real reason is that if you violate that, and this was in Garrett's too, and it was a big problem he had, and I pointed out to him, you would have two spinors going into a spinor. That's the main problem.
Ah, okay. So
That's why you want to have fermions associated to the spinor of an orthogonal group, and the bosons associated to the generators of the orthogonal group itself.
Yeah.
That's the real reason, not because you like it, because you have to do it that way. At least if the interactions are given by the commutator.
Yeah,
As I said, first of all, you have to understand what is your model of interactions, because otherwise you are making classifications that have no meaning. Because as I said, what's important is what relates particles. You can name the objects the way you want, okay? In that sense, you're free to do whatever you want. But then you have to tell me, okay, how do they interact? Now, if you make that interaction, as I said again, I'm repeating myself, that would immediately violate the fact that two spinors have to go into boson. So you violate angular momentum, very basic thing of quantum mechanics. That's the reason why you have to associate spinors with fermions and bosons to the other generators. You have to.
Yes,
See?
you're
So here
right.
is a big difference.
Yes,
I wouldn't have
stopped-
78 bosons for sure.
No, I
could
stopped at
not.
the classification level, and in fact, yes,
Yeah,
many
but-
papers I was inspired were also doing this. They were not making interaction, just classification,
Yeah, I know,
but they were able to compute the mass.
But I
and,
bet you will
but
encounter
it's not
problems. Whatever
Yeah.
model of interaction you're gonna consistently get.
I think we
I-
will
I'm
adopt your
gonna-
models.
I
And
bet you're gonna find problems right there.
yes.
Did you check, Ray, that, I mean, with the dynamic, with the standard dynamics?
No, I had
of
no
E8?
time to compute this.
Ah.
So that's the next step.
Okay.
Yes.
Because this is what I was trying to stress in the first talk. This interplay between orthogonal groups and their spinors inside E8 and the Jordan algebras. Okay, there is an interplay between those, but you cannot forget one of the two.
Yes.
So when you deal with the Jordan algebra, you still have to bear in mind who are the spinors and who are not. And you interpret them as Fermions and bosons, of course. But you have to keep that in mind constantly when you deal with E8. Otherwise, you get in trouble. As soon as you make interactions, you get in trouble. And this is one of the troubles Garrett has.
So Piero, when you think about, when you really conceptualize E8 as the union of, or as Ray said, the superposition of three copies of A8, they're not translated from one another. They're rotated from one another, and that's key. So to do operations, you're using rotate. You need things that rotate things onto
No,
the.
they are translated.
Is
They
it
are not
translated
rotated. Yes.
and not there's no. They're all parallel. Okay.
They are translated. Yes, you
They all have
cannot
the
rotate.
same-
There is no solution by rotation. By
Ah.
rotation, I was able to make D4 from 3A4, but to make E8 from 3A8, the only way is by translation.
Okay, thank you. So then the translation, if I had one copy of A8, and I focus on 8 simplices as the fundamental constructive unit, how would I take my first copy and translate it relative to the first?
So you go from the center to one neighbor,
Yeah.
and you translate by the third of this distance.
When you say the center of what? The centroid of the 8 simplex? The center of what? The center of an 8
the
simplex?
center of, yes, the centroid of the
8 simplex.
8 simplex.
Okay,
yes.
so you translate that centroid onto a near neighbor vertex.
No, onto to 1/3 of the distance which will go to a near neighbor. Yes, and you do the same to build E8 from 2 copies of D8. You translate by 1/2. So from A8 you translate by 1/3.
1/3. Huh.
It's at the end it's extremely simple, but
Right.
we took 2 years to discover
Yeah,
this.
yeah.
But yes. Yes, so yes, I don't say, in fact, I'm sure that my model is not the correct one. It's a toy model, but it's more to explain how you build it with still some good sense, because it's based on papers which exist, but they met problem and you solve them with more work, yes. So probably the H, they will have to disappear to transform into boson, and we can work together. I will try to copy your models, and I think because it's not far and
inside the 27.
it's working. Yes.
You're bound to have 11 bosons, and the rest are going to be fermions. You're bound to.
Oh yes, yes. So there will be some symmetry breaking then there, which have to
But
be
then you don't have
justified.
to remove the quarks, the extra quarks that you don't want.
Yeah, also, yes.
You don't have to worry about
Yeah.
giving them a high mass.
No, but it's good to say what is the first the first drawing, just by reason of classification and symmetry. And here it's more apparent than in the other representation. It's this, and then there is Occam's razor. Yes, it was Occam's razor, and now it's the physical razor. Yes. We need more angular momentum, the angular razor. So we made some work with Mike and Alessio also on a theory based on SU9. And So this is so now this is where I wanted to go. A kind of presentation of what we are going to do and what we can do on tensor networks. So the idea is this. This is a tensor. And it's a tensor where all dimension is 3. And in this tensor, I put E8, and I need a 6-order tensor, which is made of Jordan matrices embedded one into the other by this kind of formula coming from Tits. The Freudenthal Tits magic square, which is also very near what Mike is doing. Just a little different. Maybe there is some correction, but the principle is this: is also to have one E6 and 6 27s, and the remaining, in fact, will make a G2. If you remove one from each of the 27, you replace by the traceless version, then you get a G2. So this is a good decomposition of E8, which authorized to get Jordan matrix 27, and finally this tensor that we could use for tensor network. So it should be a tensor network which interconnect, then because it's of degree 6, it will interconnect 6 neighbors. So this is good because then we can have a grid in 3D. A square grid in 3D has a cube has 6 faces, so that will be the connector. So then I can make a cubic grid in 3D as a tensor network with E8 as intertwiner. And here is the good news, is that in the QSN, I have in some plane, I have a cubic grid, but Fibonacci spaced and not totally continuous, but I think it's still possible to populate this with a tensor network of valence 6 or of degree 6. So this is a project I propose to implement a tensor network where it's directly implemented in the QSN, but we can have E8 back into the QSN with coordinate which comes from the projection of the roots from which is come. So each point here is in the CQC, so it comes from the Elzerson quasi-crystal, and it memorizes 8 coordinates in E8. This is one point in the E8 lattice. But additionally, at this point in the E8 lattice, we can add an element of the E8 algebra to make the interactions. And then we can build a kind of lattice gauge theory of E8 on a quasi-crystal, which will be a tensor network.
So I was really attracted to whenever you talked in your presentation about the computational problem. Yes. So for us, we have an obvious pathway because the most beautiful economical way to model the dynamics of a one-dimensional quasi-crystal, such as a dynamic Fibonacci chain, is with this beautiful network, or this beautiful matrix formalism, right? Well, if you think about its degrees of freedom within its code, and then you start crossing it with point-sharing additional matrices or geometric one-dimensional dynamic 1D quasi-crystals on the plane, okay, to form some two-dimensional quasi-crystal, then you obviously restrict the code theoretic degrees of freedom compared to just one standalone. And further, when you do it in 3 dimensions, you restrict it even further. And we're interested in restriction because it's code theory. So when you think about the QSN and the Elser-Sloan and their dynamics, you can think about how one set of matrix operations defining a dynamic 1D QC is mapped into this collective setup where they all have to sort of coordinate together in their degrees of freedom, because the whole thing has to maintain its empires, its non-local structure. So that's why I think we still need to take the Penrose tiling, make it dynamic, then use the formalism of a tensor network that relates all these matrix operations, and we understand the restrictive principle, and then we can map that to the shift vector degrees of freedom that define those tensor network simultaneous, like these coordinated sets, in Z5. So once we know how to do that on the Penrose tiling as a formalism, then we will then move to doing the exact same thing with the shift vectors in E8 that define the dynamic, because the Elsner-Sloan is just Fibonacci chains. You can build the whole thing with just a bunch of Fibonacci chains, 2-letter things, and you can build that whole thing, the QSN, same thing, just Fibonacci chains.
Yes, it will be like a slice of this one. In fact, it's exactly the same.
And so it'll
this
map
one is
us-
in 3D and has a 6 connection.
Right.
And in the Penrose tiling, we will have only 4 connection.
Right. So we have these two objects, which is the tensor network as the dynamic physical space, which maps to a spin network, okay, and that they just describe one another, and then those two guys, and you can take your pick of using either one. Those two guys map to a Lie algebraic system of a shift vector code, and that's where I suspect that somehow there's 3 directions of change to animate this down.
Are we going into details on this on
Yeah.
Thursday?
Yes.
Okay.
Yes, from this, so we learn also that we will need SU3, and then we will need to have Q-treats in the tensor network, not qubits. But we can effectively work on one which is in a slice of this, which will be similar to Penrose tiling.
Yes, Ray. Okay, so this extended derivation form of E8, which is very nice, the Freudian Lattices, this can be extended to all levels of exceptional periodicity. I will note that. And
Yes.
what replaces the F4 is a higher F4, F4 prime, F4 double prime.
Oh, yes.
So I was able to write them this way. So one can actually extend this tensor network to higher levels of exceptional periodicity using that decomposition. So that's a plus.
Will be good, especially for the Leech lattice.
Yes.
Yes.
Ray, could you please explain, better, the properties of that tensor? What are the...
Yes. What is the tensor? Yes.
the tensor T with those 6 indices. What's the symmetry of...
The tensor T is made of 9 Jordan matrices.
Okay.
The 9 Jordan matrices that you have here.
Because you have 7 Jordan matrices
7,
from
and
G2.
here you have H plus and H minus. And in fact, I restrict I have
so it's
9 traceless Jordan matrices.
Okay.
Here.
So it's a tensor of Jordan matrices. I see.
In fact, T is a matrix, a 3x3 matrix of Jordan matrices.
It doesn't have any symmetry.
But I
Right.
can use this as a tensor also, because then each Jordan matrices here is a matrix of octonion, and each octonion is represented in 9 dimension by integer on the lattice.
So different than a tensor network, right?
It's
Just
a tensor, and then
yes, a tensor.
the network is connecting the tensor, so it is a tensor network.
Okay,
Tensor network, you need tensor at the connection point.
right.
Cannot be matrices.
Right.
If it's matrix, it will only have 2 connections, so it's a chain. It's not a network, it's a chain. You can, and it is used. There is a computation made with this, but also in a quantum computing, there is some parameter are free in the tensor. So it's not everything is fixed. You have something going to outside, which is why it's a Q-treat or a qubit. So you have information and you have an additional connection. This is what I explained to Fang the other day, which is the main difference between a tensor network and a spin network. A spin network is a network which is closed. The tensor network many of the points inside, which are representing quantum information, have a connection to outside, where there you can probe this connection. You can measure it, or you can input a phase to set the value. And then it's computing. And the speed network is not computing, is a way of representing a computation. And then you integrate. Yes?
Just quick question. So these JIs, the OIs, and the ZIs, are those just arbitrary vectors here, or is there any notion of what they are? I'm just curious. When you're summing up to get this T without the indices, you have the J, I, O, I, Z, I, and then JJ, OJ, and ZJ. I was just curious what those vectors are, or do they mean anything, or?
Oh yes. Either they're an E8 generator, or they are nothing, because there is also some constraints, the fact that some matrices are traceless, and that O1 is in fact real.
Right. Okay.
Yeah, so there is some of the degree of freedom diminished. They have to satisfy some constraint also. But in the general way, they are E8 generator. But if you look at all the possibility, you will have more than 248. But there is a constraint which are well known, just the fact that the matrices are traceless, and these are Jordan matrices, and this the sums to 0. So then I have this constraint.
Thanks.
Excuse me. This is the problem I always had with the Tits construction. So just look at F4. Okay?
Yes, F4. Maybe I have it on another slide.
This one. No, the first term. Sorry, you can go back to that. So is the first term.
Oh yes, okay. Just this one, yeah.
Okay,
yeah.
that's F4. Okay.
Yes.
So, before you were showing us the sort of magic star, and you were associating to the elements of a Jordan algebra, particles, a quark, whatever. I guess that would be associated, at least it is in my case, to a generator inside the 8. This disappears in this construction because that's a derivation. You see?
Yes.
H8 plus. So you have to make a correspondence not between one element in one Jordan algebra and the generator, but two elements belonging to a Jordan algebra to one single generator.
Oh, yeah.
Because you see, when you look at, I'm saying maybe in a complicated way a thing that is very simple. But when you associate a generator to a root, okay, so you do the magic star, you see the roots. But then you have to say what is a generator associated to that root. And by that you mean that the action of that generator on the algebra is the adjoint action. Here, the adjoint action, for instance for F4, is represented by two elements. They do not correspond to root, because that has to correspond to one root. You see what I'm saying?
Yes, no, they
if
correspond to,
you
here
cannot
I'm
make
encoding generators, not roots.
Sorry?
Yes, I am encoding the generators, not the roots. In this in this family of matrices, in all the H.
The construction.
Yes, I need to. Yeah.
Nothing to say about the construction.
Yes.
The problem comes when you have to associate to this action, so to this derivation, one generator associated to a root. That's why the magic star is much easier to work with respect to this one. Because with the magic star, through the symmetry function, and I can give you exactly the correspondence between one generator and one root. It's right there, and I know the action of that. Here, the action of one generator is represented by two elements in F4. Yes. How do you make the correspondence between two elements that are right there with one generator associated to one root?
Yes, I have to make this correspondence. Yes,
Yeah.
without the
Have you done
correspondence.
Have you done it?
No, I had no time.
I've
No,
tried.
yes.
It's extremely difficult. That's why the magic star. You see, I had a section in my talk saying from the magic square, which is this construction, is what is at the basis of the magic square. And I said from the magic square to the magic star. And what I meant is that that's a big improvement for practical calculations. Of course, this is a fantastic construction. I mean, Tietz, nobody could argue about the fact that Tietz is a great, fantastic mathematician. So the construction is fantastic, but it's unpractical, totally. Whereas in the magic star, you have all the numbers right there. There is no problems in calculating things. It's only a problem of time, not a conceptual problem. Here, I invite you to find a generator associated to a root which corresponds to that action. It's extremely difficult, but I tried to do it. Okay. I explained that to Mike as well. This construction is very nice, of course it is. It's Tietz, but it's not practical. In that respect, the magic star is a big improvement, huge improvement if you want to make calculations.
Right. Ray, let us know how you're tracking so that Fong can know how long.
I just have one important slide.
Okay.
And then after that, it's something less important. You can be out, it's not a problem. So next slide, I want to talk about spin network. So this is a complicated formula, but yes, this is a partition function. And Marcelo knows how to explain this. A lot of time it's integrating elements of different algebra and groups. But what is important is this is the first partition function which takes also into account fermions. So our project is when we have seen that the E8 can encode the standard model as 4A2, A2 as SU3, and also normally loop quantum gravity make computation with SU2. So if we want to go further than SU2, the initial project of Marcelo was to put D4 or eventually at the end E8. But even if we begin with the simplest one, which is SU3, it's very interesting because in the framework of this model, if we have 4 SU3, we can claim that this is a particle and that we have the standard model encoded. So we don't need really to go more complicated. And this is 3 of them are for trinification, and the third one is for the family generation. So now the problem is to try to integrate SU2 and SU3 in this stuff. So then I will explain what is this, because it's a tetrahedron.
Can you write it out in black?
Oops.
Invisible magic marker, or the magic star.
So I have a tetrahedron with three vertices and a fourth vertex here. And generally they are also connected outside. And on a tetrahedron of a spin foam or spin network, I have Lie algebra here, so it's SU2. I will write it A1. So I have a value in A1 on each of the 6 edges. And we want to also include the U here, which belong to another algebra A2. So how it's done, they put a A2 here and a A2 here, and they combine this, but the A2 comes from the vertices. So we just have to add A2 on the vertices of the spin foam, and then we can compute the integral. It's pre-computed. This is an integral on all the Lie group and Lie algebra, but in fact it's simplified. And there is the notion of 6 symbols, 6G symbols, to compute this. So there is no 6G symbols for mixed algebra, but there is a 6G symbol from A1 and there is a 6G symbol for A2. So we know that A1 can be embedded trivially into A2. So we want just to use the 6G symbol for A2 with value of A1. So we will have spin network with generally A1. And when we will have a fermion somewhere in a spin network, we will use the A2 and compute with the 6G symbol from A2. So this is a quantum fermionic tetrahedron, something new in loop quantum gravity, and I'm sure that the loop quantum gravity community will appreciate our contribution. So it's there was one, the formula comes from a paper written in 2010 or 2011, and the author is a friend of mine, so it's good. In fact, they are two. They are a couple. They are married, wife and husband, and both were researchers. But finally, research effectively in loop quantum gravity doesn't pay, so the husband became a computer scientist.
A plumber.
In Nice. And she can continue to make research. And they are Italian, both very, and a friend of Carlo Rovelli. So if we need more, I can contact them. So, but with Marcelo, we want to make a short paper on this to show our first approach, because this will permit to embed the partition function on the QSN, even with fermion. So, yes. Then also our standard model, our unification theory doesn't have gravity, which is a problem compared to, for example, Garrett's theory. But when we use it in loop quantum gravity, it's not a problem because gravity comes from the A1, and we input just the standard model and through the A2. And the A2 together make a A8 and link it to E8. So it's a very, very, very simple way of going from E8 to loop quantum gravity, of addressing one of their problems in an elegant way, based on work which has already been partially done, but they were not, they didn't choose really what algebra to take for this. And and yes, the integral, it's interesting to know what it is because it's linked to what we are doing. It's zooming on a circle, so if it's on a cycle, so I have to find a marker which is working, probably this one. So it's not a Eulerian cycle, but I have to cycle through all of the vertex, and I cannot go more than 2 times on one. But for example, I can do this. So there is different cycles which are working. So this one is one of the simplest one. So if I do this, it designs which 6G symbol I have to use, and it makes the integration of here on the cycle of this holonomy, which correspond in fact to complicated rotation to compute the take into account the curvature encoded as angle in a loop quantum gravity model, and also take into account the relationship, the internal relationship between the quantum number of the quasi-particle.
And
so
that equation is in 4D, so they are integration in SL2C, but
yes.
We are working 3D with just SU2.
Yes, maybe we can double the A1 to have SL2C, but I think if we can already make something just with one SU2 will be really the first level.
First just 3D.
And yes.
And because there are a map between functions and SU2 to functions and SL2C, so I think 3D is like a building block.
Yeah, so use the simplest formula, similar but in 3D.
So one thing to point out is, so you take Ray's tetrahedron there, and where you have your group theory, and you can just imagine, all right, well, if I wanted to transform edges onto one or the other, doing that by arc cosine 1/2, just moving it around. Yeah. But if you introduce translation operators in addition to those Clifford rotors, recognize that this here is the same tetrahedron. So you go along the vectors implied by that tetrahedron, you just take clones without changing the orientation, just zoom, zoom, zoom. You move them all away. You basically translate them all out in the direction of the vertex, the copies, such that each vertex on the inside becomes coincident with the former centroid of the original copy. So you can kind of therefore see you can get D3 equals A3 by just understanding translation operators. And then you use a strange rotor to map each of these guys and the operations on it. The Clifford, probably Clifford algebra is probably good, but whatever the operators, then basically imagine you dance around in the A3 lattice, and you have all your groups, and then you're rotating to one of the other 4 copies and using translators to the other, and those are irrational values. So the values in one are based on Lie algebraic theory, and the values to create cycles to the others are based on icosians. So it's like a hybrid. That's the whole thing about our program, is we're using crystal objects, periodic objects, relating to Lie algebras, not just the transformation of that periodic object, but in our lower dimensional space, we have the periodic group theoretic substructures that composite to the quasi-crystal stuff.
Yes, yes. So I think this is good for this project. Then if you are interested to know, because I refer to the last slide of Mike's presentation. So he was presenting a possibility to have a spectral, non-associative spectral theory. So it reminds me what you told me about Alain Cohn and non-associativity, non-commutativity. So Mike found on internet in the archives something quite fun about what Alain Cohn think about non-associativity and octonion. So I think it has an interesting historical value, and it should be there. Yes. The sound is not very good, but anyway, it's in French, so I will translate for you what is said. So it was in 2000. This is Alain Cohn. Looks a little like clay, an older clay.
Vous avez montré donc qu'avec la géométrie non commutative, on simplifie considérablement la physique d'une façon très élégante.
That's right.
Donc en fait, plutôt simple. Alors dans la même démarche.
Oh, I need to translate. Sorry. Anyway, this part is also.
No, younger Ray from the past is now older Ray is going to translate younger Ray from the past.
I think that I already saw from the web page that
Maybe if you just explain verbally to us, Ray, the essence of what he said instead of trying to go through the
yes. So I said that he showed a marvelous way of how to apply non-commutative geometry and algebra to physics in a very elegant way. And I asked if he has thought also to use octonion, because effectively when you think of algebra, non-commutativity, it's a quaternion, and the next one is the octonion. Yeah. And then he will answer.
Was that really you in the audience?
Oh, yes.
Oh, I thought somebody was joking. That was, oh, wow. Wow.
Yes. Who else can ask this question? Talk about
That's why I was going with the younger Ray, because it does kind of look like a younger Ray.
a younger Ray. So time travel.
But is that really you on your like LinkedIn page or something with by the swimming pool with the sunglasses?
Yes.
Okay. You were sexy.
Younger Ray and sexy
Did you see that
Alessio.
picture? Respect, like it's a whole new level of respect.
So, so then his answer is very interesting. He said, I can explain just now. Why? Because language is associative. You need associativity to be representing an operator on something. And at the end, he said, when I'm thinking of non-associative, I have the same reaction that many mathematicians have when they are thinking about non-commutative. You understand the joke? Yes, but finally, I'm happy that we are working in non-associative because his non-commutative work was a big success, even if at the time he had difficulty to communicate on it.
And of course, he says the quintessential example of non-commutative geometry is the Penrose tiling.
So I was very happy. You can understand this as he says that non-associative geometry, or what we want to do, is to non-associative non-commutative geometry what non-commutative geometry is to basic mathematics. So yes, but in another way, he also showed a little that he didn't like it. But I tried to push him to work on this, and just so after that, I was at some of his lecture, and well, one time they asked me a question. Oh, you the Octonian specialist, can you you answer?
We've seen the virtues of non-commutativity. So the time is right to see the virtues of non-associativity.
Yes, it takes 20 more years, you see.
Sure. And in 2040, we're going to be studying non-alternative geometries.
Yes. In Fermions, you can stop there.
So Ray, would the algebra of the Elser-Sloan quasicrystal, clearly it's non-commutative, but is it also non-associative? It's based on icosions. Would it be also
yes, it depends how we apply the algebra.
Okay.
If it involves Octonian multiplication, it will be non-associative. If it's only the Lie algebra, I think it's associative.
Well, it's not a Lie algebra, is it?
Yes.
It's based on the Elser-Sloan would distinctly not be a Lie algebra. It is some other icosion-based algebra, but I'd love to know if Remy Masori or anyone else has written down the algebra, because algebras have been written down for lower dimensional quasicrystals. But I would just be curious.
I was thinking the algebra of the dynamic.
Oh,
yes.
Well, yeah, the phazon. Oh, right. But still, it's clearly non-commutative because the algebra of all quasicrystals is non-commutative. But I don't know if it's also non-associative. Like the Penrose tiling, you can look up papers on the algebra. It's non-commutative.
I think because what he said, because the language is associative. But then a code should be non-associative.
Okay.
This is the difference.
Okay.
So he answered to your question also.
And a quasicrystal dynamics is a code by definition.
Yes.
By strict.
A code
thinking.
is less strict. And I think I have a last slide to show. Okay, here.
So you were 14 in that video, so Elaine Cones must be 100 years old by now.
No, she's 75 now.
Okay, well, I was off by 25 years.
But yes, he is now retired. He gave his last lecture at Collège de France last year. And he stopped his chair, and he was there since '84. So
he created a nice body of work, right? He single-handedly created non-commutative geometry in a sense. you know.
Yeah, and she was quite the best mathematician in France since between '84 and last year. Because also the share that he has in Collège de France is the most honorific position. So,
my understanding
but
is
he's
very
still good in
difficult,
maths
his
because
program, his mathematical physical unification. My understanding is very, very steep learning curve.
There at his lecture, I met Pierre Cartier, which is one of the founders of Bourbaki. And I think he's more than 80, and he's still very, very good in mathematics. So just the last slide, but it's not so important. It's when I see so this other slide, there's the slides that I presented at Prague, the end of my presentation, but I will not make them here. And all the slides that I presented today were new for today, yes. So this is a backup, this is with an old slide. And in fact, I was this picture, so maybe it's quite similar to what you presented with the cube-octaedron and the Merkaba. And this is where we find the 3A8 lattice and the magic star inside of the QSN. Yeah. So we are there. Yeah. So there is also cube-octaedron in the QSN from the 3A8 lattice. So to illustrate the 9-dimensional coordinates and the 8-dimensional coordinate equivalence of different points. So maybe I can zoom on it a little more. And on this, it's finished. So thank you for your attention.